Hey y'all, we are Memphis University and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. Today we're going to be continuing our advanced derivative unit and we're going to be doing maybe the most advanced derivative topic of them all, which is going to be related rates. So a lot of students fear related rates, but once you practice and get down the process and sort of know the strategies and the hints for these questions, you will be able to master these questions just like everything else. So what is a related rate problem? Basically, there's going to be a couple variables that are going to be related, that's why it's related rates, by some sort of equation. And then what we're going to do is we're going to take the derivative with respect to time, because time is going to be the variable that governs these variables. And then once we take that derivative, we're going to see how the rates of these quantities are related. How are they changing with respect to each other and things like that. So keep in mind that a lot of times these questions do come from the real world, whatever that means. So we might have a ladder sliding down a wall, we might have two cars heading toward an intersection, we might have some sort of person watching a balloon from afar away and the angle is changing and things like that. So there are a lot of famous related rate questions that do repeat themselves that appear on the AP exam, not as a free response question itself, but as a multiple choice question and part of a free response question. So that's what we're going to try to do today. We're going to do this in three sort of phases. The first thing we're going to do is we're just going to list out the steps of related rate questions. Then we are going to give some hints on how to do related rate questions, a few hints that I feel are useful, especially trying to catch the most common mistakes that students make. And finally, we're just going to do several examples. Again, some of them will come from the real world, so you might do the ladder question and things like that. So let's get started. So again, what we're going to start off with is steps. So these are the related rate steps, first of all. So related rate steps. So the first step is, I think, a pretty important step, which is draw a picture of a situation. Because again, you might have some cars coming together, you might have a ladder sliding down, you might have that balloon rising beautifully, majestically into the sky. So oftentimes it's good to draw a picture. So we're going to draw a picture when necessary. And the point of the picture is to come up with some formula. So sometimes they give you the equation that are nice. That's going to be the first example where we're just going to start off with the equation. But sometimes they don't give you an equation, and what you have to do is you have to come up with equation, usually geometry. So come up with equation. So these formulas could be area is equal to pi r squared, the area of a triangle, some quaternion potentially if you're dealing with angles, and then the big one is usually the Pythagorean Theorem, a squared plus b squared equals c squared. Keep in mind though that of course there's some harder shapes like 3D shapes, cones and spheres, but usually on the AP exam they give you those formulas for you. So once you have the equation, the most important step by far is step 3, which is take the derivative of everything with respect to time. So take the derivative, but implicitly, so we have to review a little bit of implicit differentiation with respect to time. So it's strange that you're not going to see the letter T in these formulas. You're going to see something like pi r squared because you have the area of a circle. But just keep in mind that every single variable, even x in this case, has to be taken with the derivative with respect to time. So the derivative of x squared isn't our normal 2x. It's going to be 2x times dxdt, as we see throughout these questions. So this is one of the rare cases where when x is not the variable you're taking the derivative with respect to, you're actually taking the derivative with respect to time. So just be wary, every single variable you need to implicitly differentiate with respect to time, as we'll do in all the examples. Also keep in mind that we're taking derivatives, so if you need to do the product rule and so on, the chain rule is really with that derivative with respect to time business, then you have to do that. Then you're basically good to go at this step. What you can start doing is you can start plugging in numbers. So plugging in numbers. You're going to have like 5 variables or so. So what I do is I like to find the variable that I'm trying to solve, and I'm just start plugging in givens. These are givens into the question, and just keep going until you get to the answer after you take the derivative. The 5th step is sometimes you have one last number to plug in, and it's not a given. So you're like, how am I going to be able to plug in this number? I need this one last number. And how you usually do that is usually use this original equation from step 2. So you're going to use the original equation probably. And by now you should be able to solve for your variable. So that's the last step. So I guess we can write step 6, solve. So a pretty repetitive process again. We're going to draw a picture if the picture helps us. We're going to come up with an equation. Potentially it's going to come from geometry like the Pythagorean Theorem. And then we are going to take a derivative with respect to time. That is key. Everything has to be taken with respect to time. So we need to implicitly differentiate. So anytime we take a derivative, it's going to have times dx dt or times dy dt or times dr dt, dA dt, whatever. They're all going to be times something. Then we're going to start pulling in givens where they go, which is actually a pretty difficult step because not only do you have to plug in givens, but you also have to be careful of negatives. Finally, what we're going to do is we are going to, if we have one last variable to solve for, and it's not given, we're going to use the original equation and we should be able to solve for it. And finally, we should be able to solve for the quantity that we need. So one of the difficult things is, again, there's a lot of variables. So you want to be pretty, you want to think pretty critically, which variable do I want to solve for? Which variable does each given go to? So one of the things we're going to talk about before we talk about actual questions is we're going to talk about hints for these questions. And mainly it deals with plugging in. So now that we know steps for related rate questions, we're going to go over hints for related rate questions. So these are hints for related rate questions. Related rates. So the first thing is in terms of plugging in. So one thing that students do, unfortunately, is that they'll plug in too many variables before they take the derivative. And then when they take the derivative, then they won't have anything to take the derivative of, which basically. So the rule is you can plug in things that are not changing. So before the derivative, plug in quantities that are not changing. For example, when we did the ladder question, the length of the ladder won't be changing, so we can plug in the length of the ladder immediately into the question. But we're not going to plug in anything that does change. So don't plug in quantities that do change. Because you want to make sure that you're going to be able to take its derivative. And if you plug in a number for a variable and that variable is changing, you're not going to be able to take the derivative. So don't plug in quantities that are changing. Quantities. So that's our first hint. Our second hint deals with plugging in things. Again, plugging in is a really difficult step because there's going to be so many variables that we're going to be dealing with. The main thing is that rates go with derivatives. So when you plug in, rates or how things are changing are going to go with derivatives. And then things that are not rates are going to be things that are not derivatives. So for example, if you have r and r prime or r and dr dt, your rate's going to go into dr dt and your radius is going to go into r. Keep in mind that when you're plugging these in, again, there's a lot of difficulties in terms of negatives. So when you have rates and rates go with derivatives, when you have these rates, what you want to be aware of is which one is negative and which one is positive. And it's not based off what direction you're going, it's based off whether the quantity it represents is getting smaller or bigger. So if the thing is getting bigger, if the quantity is getting bigger, that means your rate's going to be positive. So for example, a circle expanding, or you're going away from an intersection and the distance between you and the intersection is getting bigger. It doesn't matter if I'm going north, south, east, or west. So if the quantity is getting smaller, that's the hardest part. That means that your rate is going to be negative, meaning your derivative is going to be negative. And it's very difficult to see because in the question, there's not going to be a negative number, so you have to put a negative number into the question. Finally, if a quantity isn't changing, that means its rate is going to be 0. Because it's not changing. So its derivative, the number you're going to plug into that derivative, if that quantity is still there, is going to be 0. So those are our main hints for related rate questions. Again, let me repeat. Try to not plug in things too early because you need to be able to take the derivative. Try to plug in after the derivative. It's take the derivative, then plug in. But you are allowed to plug in quantities that are not changing because the derivative of those quantities will be 0. Then, when you're plugging in things, just be very careful because there's going to be a lot of variables. Another hint is that anytime you have a rate, that's going to go into derivatives. Things that are not rates, those are going to be in the not derivatives. Finally, when you're dealing with rates, this is probably the biggest error. Just keep in mind that the sign of the rate is very important, or the sign of the derivative. If things are getting bigger, balloons are expanding, or cars are going away from each other, the ladder is sliding away from the wall, these rates are being positive. But if things are getting smaller, those rates are negative. The ladder is sliding down the wall, something is contracting, you're going towards the intersection, something like that. Finally, if the quantity is not changing, usually people know that that rate is 0. So let's try to do some actual examples now that we have steps and hints. Remember that it's going to be find a function, potentially drawing a picture. We're going to take the derivative. Everything needs to be implicitly differentiated. And then finally, we're going to start plugging in stuff. So let's do the first example. So the first example, I'm trying to erase this. My board's a little dirty today. So I'm trying to erase faster. So in our first example, we're going to already have the equation, so we don't have to draw a picture. So my equation is going to be 5 plus a squared equals 2ab. And there's going to be some givens. So the givens are that a and b are related in time with respect to time. So now we know we have a related rate question. Again, the key variable actually isn't on the board. It will never be on the board, but just remember you have to take the derivatives with respect to that, and that's time. So notice there's no t's in the equation, but we're still going to have to do implicit differentiation. Finally, what we know is at t equals 2, at t is equal to 2, we know that dA dt is equal to 5, is equal to 5, a is equal to 1. So these are going to be numbers that we're going to plug in, and we're going to try to find dB dt. So let's do that. So again, let's just go through the steps, and hopefully as you go through the steps, you'll sort of have an idea of what's going on. So we're going to write our equation, 5 plus a squared equals 2ab. And all of the next questions, we're not going to be able to have this equation starting off with. So this is a nice way to savor this. We didn't have to do anything for this first step. The key step though in this question will be taking the derivative. The derivative of 5 of course is 0, but the derivative of a squared, again because you're taking the derivative implicitly with respect to t, isn't just going to be 2a to the 1 because of the power rule. We do need to multiply by dA dt. And you're going to get very used to this as related rate questions. Every time you take the derivative of a variable, you have to take the derivative with respect to t. Finally, we're taking the derivative of 2ab. And again, if you need to use the product rule, you need to use the product rule. Just be wary that this 2 should be on both sides of the product rule. So first off, I'm going to keep the same, 2a. Then I'm going to take the derivative of b. But again, it's not just 1, it's dB dt. Then I'm going to take the derivative of the thing I kept the same. So what's the derivative of 2a? Again, it's 2a. It's not just 2, it's 2 times dA dt. And then finally, the derivative of the last part of the product will just keep the same, so it's going to be times b. So this is the derivative, and you're going to be taking very similar derivatives throughout these sort of questions. Just slowly taking derivatives and trying to find the derivative carefully when you implicitly differentiate with respect to everything. With respect to t, sorry, of everything. So now that we have our derivative, now it's just the game of plugging in things. So I like to box the one I'm trying to solve for. So it looks like I'm trying to solve for dB dt. So I'm going to box that one. And then I'm going to start plugging in stuff. So it looks like I have dA dt, which is 5. That's lovely. Or sorry, dA dt is 5. That goes over here. A is given as well. So notice that they do give me a lot of givens. So I just start plugging it into the question. Then this A is 1 as well. I'm not going to plug in anything for this quantity because that's the thing I'm trying to find. And then finally, dA dt again is 5, but it looks like I have b left. So this is where students sort of mess up. Here, I'm actually trying to be tricky. I'm trying to trick you, trying to make you fail. I'm giving you this t equals 2 value as an extraneous information. So usually on the AP exam, they don't give extraneous information, but in this case they do because they want you to plug in t equals 2 into this b. But remember, our last step is that if you have one last variable to solve for, you don't want to plug in t equals 2 because that's not b. What you do is you use the original equation. So if you use the original equation and you plug in a for 1, notice you'll be able to find b. 5 plus 1 equals 2 times 1 times b. I'm plugging in a is equal to 1 into this equation so that I can solve b. It looks like b is equal to 3 because it's 6 divided by 2. So just don't fall for that trick again. Keep in mind that I'm trying to trick you. I'm a teacher, I'm evil. I'm trying to make you plug in the t equals 2 number, but that's not the case, of course. What you need to do is, and you'll see this in all these questions, you'll have one last variable to plug in. We were able to plug in a and dt just from the givens, but the givens won't be sufficient enough. We'll have one last one, but we're gonna be able to plug in the givens into the original to find that last one. Finally, all you have to do is solve. So it doesn't look like this one is too bad to solve. Looks like it's going to be 10 minus this thing, so minus, let's do some math. I believe this is 30. And then finally, we're going to divide by 2. So it's going to be negative 20 over 2, which is negative 10. So keep in mind that for this question, again, you can have negatives. It just means your thing is decreasing. So this is the answer. So hopefully you saw our process. We didn't have to come up with a formula because the formula was given. Two main things. We took the derivative, and as we took the derivative, everything had to be taken with respect to t. So that's why we have dA dt, that's why we have dB dt, and so on. We took the derivative product rule. Then we started plugging in things, and we were sort of having a lovely time until we got to this variable right here. And at that time, what we did is we used the original. And that's how we did these questions. So it's going to be the same thing every single time. We're going to find a function, take the derivative with respect to t, start plugging in stuff. So let's do this again. So let's see if I can erase a little bit faster this time. So let's erase. So let's say we're going to have a circle this time. Because again, remember that usually in these questions, there's some sort of geometry situation going on. So let me erase this. So for the next question, I'm going to have a circle that's expanding. And let's say it's expanding at a rate of something like 16 pi, no, let's say just 2 meters per second squared. No, meters squared per second, because area would be in meters squared. So we have this fact, the circle is expanding at a rate of 2 meters per second. And what we're going to do is we're going to try to find the rate of change of the radius when the area is 16 pi. So in this case, we probably don't have to draw a picture because it's just a circle. But this is our first real world example, or at least geometry example. So what you need to do at the beginning is you need to come up with a formula. So in this case, because we're dealing with the area of a circle, we're going to use the area of a circle formula. And that's a formula that you're expected to know on the AP exam. You don't need to know, again, 3D shapes, but you do need to know your basic 2D shapes. So in this case, it's going to be A equals pi r squared. So then what we're going to do is we're going to take the derivative. So when we take the derivative, again, just be careful. The derivative of A isn't just 1. The derivative of A is dA dt. Because the derivative of any variable is changing with respect to time. Because as time is going on, this circle is expanding. Then we're going to take the derivative of pi r squared. Again, it's the power rule. So we're going to take the 2, drop it to the front, 2 pi r. And then just keep in mind that this is not the derivative. It needs to be multiplied again by dr dt. You'll get used to this pretty fast though. Everything needs to be taken with the derivative with respect to time. So now it looks like all we have to do is start plugging in things. Again, I like to sort of box the thing I'm trying to find. In terms of our hints, remember that rates go with derivatives. So this is a rate, so it'll be either dA dt or dr dt. This is a rate, so it'll be either dA dt or dr dt. They wouldn't go into the variable r, for example. So let's see this. So it looks like the circle is expanding at a rate of 2 meters per second. What I mean, of course, is that the area of the circle is expanding, so we can maybe change the wording of this to be a little bit more precise. But the area of the circle is expanding at this rate, so that means that this is going to be 2. looks like we're going to be solving for the rate of change of the radius. So keep in mind that we're not solving for the radius because that would be finding the radius. We're finding the rate of the radius. So just as we said before, rates go with derivatives. So we're trying to solve for this quantity right here. So I'm not going to be able to plug in anything. Then it looks like we have to find r, and this is where our last step comes in. Usually we have to solve for one last given, and that one last given is given by the original. So if our area is 16 pi, we can put units on here if you want, meters squared. Then that means that we can use that to find our radius. So we have 16 pi equals pi r squared. Looks like the pi's are going to cancel, and then when you take the square root, because radiuses have to be positive, looks like our radius is going to be 4. So it's the same thing as the last question. We have one last variable to solve for, so we use the original. We're not going to panic. We're going to use the original to find that last variable, and then we're going to plug it in. So in this case, it's going to be 4. So finally, what's the RDT? Looks like it's going to be 2 divided by this quantity right here. The 2's will cancel. So I believe we have 1 over pi 4, or 1 over 4 pi. If you want units, we can put units. That unit is just going to be meters over seconds, because that's how it's going to be changing. So this is the first real related question, and keep in mind that it wasn't too bad, of course. All we did is we identified a function, we took the derivative, everything needs to be derived with respect to time, and finally we started plugging in things where the last variable, we used the givens and the original to find that last given that we need so that we can find the quantity we want, which in this case was the RDT. So let's just keep practicing. Maybe we'll do 3 more examples and we'll do some more famous questions. So let me erase this. So erase this. I don't know why my board is so dirty today, but perhaps it doesn't want to do really great questions, but we are going to persevere. So let's say we're going to do the famous ladder question now. Unfortunately, the ladder question does involve a big paragraph and in terms of writing it out, and that's why some students have a lot of trouble with this because they have to interpret all these English words, but let's write the ladder question. So a ladder, if I can spell the word ladder, let's say it's 5 meters long. It's going to be sliding down a wall. The top of the ladder and the ground of the ladder, the rate that which is changing is 2 meters. So the rate, let's say we can say it's sliding down a wall at a rate of 2 meters per second. Again, this means that the distance between the top of the ladder and the ground is changing at 2 meters per second. And then what we're going to do is we're going to try to find the rate of change. So even if I'm writing these words down, you're sort of thinking about what we need. Rate of change means we're going to be finding a derivative at some point. So find the rate of change of the distance between the wall, so the wall, and the bottom of the ladder. When this distance is 3 meters. Again, these questions are really difficult. It's not just math like the first example where we can just start taking derivatives or a simple shape like a circle in the last example. What we have to do is we have to come up with a situation and turn the situation into math. Once we have the math, you'll see that the math is actually not that bad. So what we're going to do is we're going to first draw a picture, because again, I feel like a picture is pretty helpful when we're doing this. So I have a wall here. Hopefully you can tell that this is a wall. Then we have the ground. How lovely. And then finally, we're going to have a ladder. I'm going to draw a very beautiful ladder. This is going to be my ladder. And basically what's happening is that you're going to have this ladder represented by my marker here, and it's sliding down the wall. So there's going to be 3 main distances that we care about. First, we care about the ladder's length. We're going to call that C, because we were about to use Pythagorean Theorem. Sorry to spoil things up. But the ground is going to be represented by A, and then finally the wall is going to be represented by B. So we have A, B, and C here. So this is the situation. The ladder is sliding down, and we're going to find some sort of rate because we want to find the rate of change, and that will be a derivative. So what formula do we use? Keep in mind that when we have triangles, there's going to be various options. Sometimes it's going to be SOHCAHTOA because we have angles. Sometimes it's going to be 1/2 base times height because we have areas. But just keep in mind that when you have these right angles, it's going to be the Pythagorean theorem. So the formula we're going to try to take the derivative of it is a squared plus b squared equals c squared. So the first thing is going to be taking the derivative, and the derivative actually isn't bad. Again, if you remember to take the derivative with respect to t, you should be good to go. So the derivative of a squared isn't just 2a, it's 2a times dA dt. What's the derivative of b squared? Well, it's 2b times dv dt. Keeping in mind that notice that I'm not plugging in any numbers right yet because I think that it's better just to have the function and then take derivatives, especially because this derivative isn't that bad. So I just took a bunch of derivatives. What some people start doing wrong is that they start plugging in variables again, and then when they take that derivative, they won't have any variables to take the derivative of, so then they're not going to know what to do. So I like to have the formula and then take the derivative. Now let's try to recognize what quantity we're trying to find. So it looks like, again, we're trying to find a rate of change, and it's the rate of change of the distance between the wall, so the wall, and the bottom of the ladder. So it looks like we're trying to find dA dt in this case. So I'm going to box that. I think it's a useful step because I know that I'm not going to be able to plug in a variable, and if I know my target, I'm going to be able to find it better. So now what we're going to do is we're going to start plugging in random things. So first off, we're going to plug in, looks like we have a, because a again represents the distance between the bottom of the ladder and the wall. And keep in mind that this distance doesn't have the word rate, it's just the distance is 3 meters. So we know that it goes not into a rate, as our hint suggested, but it goes into a variable, and that's going to be a. So it's going to be 2 times 3. We're not going to be able to plug in anything for dA dt because that's the quantity we're solving for. Then we're going to go over here. Doesn't look like I have another non-rate, so I don't want to plug in anything for b just yet. We might plug in something later on, of course. What's the derivative of dB dt? Well, dB dt is a rate. It's a derivative. So it's going to be the derivative of this quantity b, and keeping in mind that the quantity b represents the distance between the top of the ladder and the ground. So dB dt is going to be actually 2, but it actually isn't 2. This is where it gets really, really tricky. It's actually going to be -2. So let's write -2. Because remember our big, most sort of mistake on these questions, that when you're plugging in rates, they might not have negatives or positives, but you have to determine whether you want to plug in a negative or positive. And it's based off increasing or decreasing. Something is increasing when the derivative is positive, something is decreasing when the derivative is negative. So notice that as the ladder is sliding down, this distance is getting smaller and smaller and smaller because the ladder is sliding down because of gravity. So that means that dB dt is negative. You have to put -2 here or else you'll miss the question. So finally, we're going to keep plugging in. So when C is going to be the length of the ladder, it's the hypotenuse of this triangle. So it's just going to be 5. And then finally, dC dt, that's the rate at which the ladder is changing. But keep in mind, the ladder is not getting any longer. So its derivative would be positive, or getting smaller. So its derivative would be negative. So its actual derivative is 0. As we mentioned before, you could have actually plugged in this 5 into C at the very beginning of the question before you take the derivative, because you're allowed to plug in variables before you take the derivative of things that are not changing, not things that are changing. So in this question, it would have been allowed to plug in C for 5, but it would not have been allowed to plug in 3 for A, for example. So it looks like we plugged in all of our things. So now we have one last variable to go, B. And what we do is we use our original because B is not given. That's the last step in most related rate questions. Use the original to find your last given. So in this case, it's going to be a 3, 4, 5 triangle. It usually is a 3, 4, 5 triangle. 3 squared plus 4 squared is equal to 5 squared. So because we know it's a 3, 4, 5 triangle, this quantity B is going to be 4. So now it looks like we're ready for the answer. This is 0 because, again, the ladder's not changing. So that's why dC dt was 0. So we're going to bring this to the other side. So it's going to be 2 times 4 times 2 over 2 times 3. That's going to be the answer. Let's try to simplify this a little bit. So it's going to be, looks like it's going to be 8 over 3. But hopefully you see sort of the idea of what's going on. Same thing as our previous examples, even if it was slightly harder. What we did is we identified a function, then we took the derivative with respect to t. Just like normal, you're going to be taking the derivative of the Pythagorean Theorem, so you'll get very used to this. The harder thing is to plug in all these variables. Rates go into derivatives. And remember that rates are also pretty tricky. Sometimes they're negative because they're represented some quantity that is decreasing. So in this case, this dB dt was negative. But as long as you know that, and as long as you know that the last variable potentially is found using the original, you should be okay with these sort of questions. So let's do a SOHCAHTOA question, something involving angles now. So let me erase this. Let me erase. Let's do another question. So let's say we have some person, let's say we have John or somebody. And John is watching a balloon rise because he likes to watch balloons rise. So he's watching a balloon rise vertically. And let's say this balloon is rising at a rate of 5 meters per second. So he's watching a balloon rise vertically at a rate of 5 meters per second. If John is, let's say he's 12 meters away. What is the rate of change of the angle between, I can say the angle of elevation, when the angle is, say, pi over 3. So again, when you have these questions, what you want to do is you want to draw a nice picture. So it looks like we have a picture of John here. He is going to be 12 meters away from this balloon rising. Here's my little balloon. It's rising, of course. It's going to draw an angle, draw a nice little triangle. And this balloon we know is rising at a rate of 5 meters per second. So this is the angle we care about, theta. And looks like we have the situation sort of in this question. So in this question, we do have a triangle, keeping in mind that, again, triangles are kind of complicated in these related rate questions because there's a lot of options to do. But because we have an angle, what we're going to do is we're going to try to employ SOHCAHTOA. So SOHCAHTOA itself is pretty complicated because it's sine, cosine, and tangent, so we have to decide which one we want to do. But because it looks like this side is important and this side is important and not, for example, the hypotenuse, looks like we should be doing tangent. So the formula I'm going to do is I'm going to write tangent of theta, and then let's sort of attribute some variables for this question. So I'm going to call this x because it looks like the x side. I'm going to call this y. So it's going to be y over x. So this is going to be the formula that governs this question. And what I'm going to do is I'm going to take the derivative of this formula and try to solve this question. So keep in mind, though, I can save a little bit of time because remember that you can plug in certain variables, but you don't want to plug in all the variables. So the variables you can plug in are the numbers that are not changing. So keep in mind that John here, this is John. John is always going to be 12 meters away horizontally from this balloon. He's not running back and forth, for example. So I can plug in 12 for this y, for this x here, not y. And this is going to make the derivative a lot easier to solve for. If I were given a y distance, I definitely wouldn't want to plug in that number because that number is changing. Y, the quantity that y represents, which is the distance between the balloon and the ground, is certainly changing. The balloon is rising. Again, I'm allowed to plug in x because that distance is not changing. It's consistently 12. John is not moving. He's just observing this balloon rise in the air. So that's going to be that. So now we're ready to take the derivative. So again, we don't have to do the quotient rule because we're taking an easier derivative. The derivative of y over 12 is the same thing as 1/12 y. So the derivative of 1/12 y is 1/12 y prime, or dy dt. Again, of course, you have to be consistent with these sort of derivatives of any variable. It has to be with respect to t. Then what's the derivative of tangent of theta? Well, that's going to be secant squared of theta times d theta dt. So what are we going to try to find? Well, it looks like we're trying to find d theta dt because we're trying to find the rate of change of the angle of elevation. We do know the angle, so now what we need to do is we just need to start plugging in variables. And it looks like in this case, we don't even need to use the fact that we need to use the original to find our last variable, because it looks like all the variables are given to us. First off, pi over 3 will go into theta because that's the angle, and it's not a rate, so it's just going to go into a variable, theta. And then it looks like 5, which is a rate of the vertical rise of the balloon, that is going to be a rate, so that's going to go into a derivative, that's going to go into this slot right here. So it's going to be 5/12. And it looks like, again, all I need to do is find secant squared of pi over 3. That is somewhat tricky, so I'm going to find that first. Whenever I think about secant, I'm going to find cosine of pi over 3 instead. And I'm going to do 1 over it. So if you remember your unit circle things, cosine of pi over 3, well, pi over 3 is the bigger angle, so that means that you're doing adjacent over hypotenuse. When you have the bigger angle, the adjacent side is the smaller side. So I think this is going to be 1 over 1/2 squared. So this is just trying to find secant squared of pi over 3, so a little bit of trig. 1 over 1 over 2, that's going to be 1 over 1/4. And then 1 over 1/4 is 4. So that's just a little bit of computations to find secant squared of pi over 3. So it's going to be 4 times d theta dt. So what's our answer? Well, our answer is going to be d theta dt is equal to 5 over 48. Radians per whatever the unit is, seconds. So that was a nice little angle question. Let me just recap it. When you have angle questions, oftentimes the formula you're going to use is SOHCAHTOA. In this case, because we have these two sides were most important, where we decided to use tangent. Another big thing is you can make your life a little bit easier, but try to not make your life too easy, which is that you can plug in quantities that are not changing. So that's why we plugged in 12 for x, but we certainly did not plug anything in for y, because y is definitely changing. Then we took the derivative just like normal. The derivative didn't require implicit differentiation, and then we started plugging in things, keeping in mind that we had to do a little bit of trig at some point. We had to find the secant squared of pi over 3, but that's the same thing as 1 over cosine squared of pi over 3. Cosine of pi over 3, I believe, is 1/2. So it's 1 over 1/2 squared, which is 1 over 1/4. And that's how we did the question. So let's do one more question, sort of the famous inverted canonical tank question, and then we should be good to go. So I'm going to erase this. One last question. So these related questions, hopefully you see that, again, they're the same thing every time. You find a function, you take the derivative, you start plugging in things carefully. So let's do this. One last one. So we have a tank, a water tank, that's an inverted cone. The height of this tank is, whose height is, let's say, 4 meters. Its radius is, let's say, 2 meters. The question is, find how fast the height is changing, or the water level is changing, when the radius is 3 meters. And the volume, or the amount of water that is in the tank, is changing at a rate of, let's say, I'm not sure, 2 meters per second. So, or 2 meters squared per second, or 2 meters cubed per second, actually, because we're dealing with volume. So when the radius is 3 meters and the volume changes consistently at 2 meters cubed per second. So this is going to be my question. Kind of a difficult question if you don't know how to do this question, so I'm going to work it. You have this funnel here, or this inverted cone. The height is going to be, let's say the height is 4 meters, the radius is 2 meters, and we're trying to find this level right here. So there's water in this tank, and basically water is coming into the tank, and what we want to do is we want to see how fast the water level is changing. That represents the change in the height of the water when the radius is 3 meters, and as water is coming in, water is trickling in at a rate of 2 meters cubed per second. So first off, we do have to come up with a formula, but because we're dealing with the volume of a cone, the formula is going to be the volume of a cone. So it's going to be V equals pi times 1/3 pi Hopefully my marker doesn't die at the very end of this video, but it's 1/3 pi r squared times h. And again, you don't need to be expected to know these 3D sort of formulas as long as you're taking the AP exam. Maybe in college calculus exams you would be expected, but on AP exams they usually give you this formula. The problem with this formula is that it's going to be hard to deal with both variables r squared and h. So what we can do is we can do a little bit of a trick to change this formula and to be in terms of one formula, and then we take the derivative. I only know how to do this trick or know why to do this trick because I've done this question before and I've seen the answer. So basically what we're going to do is we're going to take a cross section of this cone. It's going to look like this. Notice that this height is, the radius is 2 and the height is 4 of the entire cone. And if you take the water level itself and call this r and call this h, so there's 2 heights and 2 radius. The first radius is the radius of the cone itself, the entire tank, and also the height of the entire tank. And then we have the radius and the height of the water level. And keep in mind that if we have this sort of picture, we can use our old friends similar triangles in order to have a formula of h with respect to r. So our formula is going to be r over h. R over h is equal to 2 over 4. So I'm going to be able to solve them. And again, the point of why I'm doing this is to make this harder formula to be in terms of just one equation or one variable. So it's going to be 4r when I cross multiply equals 2h. So it looks like r is going to be h over 2. So again, what I'm going to do is I'm going to make this formula a little bit easier before I take the derivative. It's going to be pi times h over 2 squared times h. So now I'm ready to, I'm actually not going to be ready to take the derivative. Let me try to simplify this as much as possible before I take the derivative. V is equal to 1/3 pi h cubed over 4, keeping in mind that h squared times h is h cubed, and this 2 is also being squared. So then we have v is equal to 1/12. I don't know why I wrote a pi there, but 1/12, 3 times 4 pi, times h cubed. Again, my marker is dying at the very end of this video, but I think we're going to be able to survive. Let me sort of dry this out. So it's going to be 1/12 pi r cubed. And now we're going to take the derivative, and you'll see that once we take the derivative, the question will be very easy. So we're going to have dv dt is equal to 1/12 pi. And what's the derivative of h cubed? Well, it's 3h squared times dh dt. So 3h squared times dh dt. 3h squared times dh dt. So again, just our normal derivative of h cubed. The derivative of h cubed isn't just 3h squared, it's 3h squared times dh dt. So now what we need to do is we need to start plugging in variables, keeping in mind that we're trying to find how fast the water level is changing. That's going to be dh dt. Then we need to start plugging in variables. Well, dv dt is 2 because that's how fast the volume is changing. So it's going to be 2 is equal to something. And finally, we have one last variable to solve for. Remember, if you have one last variable to solve for and it's not given, usually you use the originals. Keep in mind that it's not this height 4 because that's the height of the entire thing. What we're going to do is we're going to use the fact that the radius is equal to 3. Well, if the radius is equal to 3, notice that the height, so we have the formula r is equal to h over 2. So if the radius is 3, that means the height is going to be 6. We're going to cross multiply that 2 and make 6. So it's going to be times 6 squared. And then we're going to have the variable that we need, dh dt. This is getting a little bit messy, but we're going to be able to finish the question finally. So all we have to do now is to sort of simplify things. 6 squared over 12 is 3 because it's 36 over 12, which is 3. You're going to have 3 times pi, so that's 9 pi. So the final answer is going to be 2 divided by 9 pi. So we can just write the answer randomly, and I don't know where to write it actually. We can just write it right here. 2 over 9 pi is the answer. So hopefully that makes sense. The work here was pretty unorganized, but hopefully you were able to follow along. Again, you have this tank and you use this similar triangle business in order to convert this harder function and to be in terms of an easier function. Once you do that, it's the normal related rate process that we talked about throughout the video. You take the derivative where the derivative needs to be with respect to time. So that's why this dh dt is here. Finally, when you have one less variable to solve for, usually use the original. In this case, the original was sort of the similar triangle business. So because they gave us the fact that the radius is 3, we were able to find the height. The height was going to be 6, because 6 divided by 2 is 3. That allowed us to plug in all the variables we needed, and we were able to find that the final answer was 2 over 9 pi. But that's our related rate video. Again, it is a pretty tricky business, but if you follow the steps and follow our hints, you will be able to master this eventually. So again, the steps are locate a function, potentially through geometry, then take the derivative. Everything needs to be taken the derivative of with respect to time. So you're going to have dr dt, dx dt, dy dt, and so on. After you do that, you just start finding what you need by plugging in all these little constants here and variables. Keeping in mind that derivatives go with rates. Also, when you're plugging in, just be careful. If something is decreasing, that means its derivative will be negative, even if negative is not in the question as the given. Finally, if you have one less quantity to solve for, usually use the original. But again, because related rates questions are so hard, a lot of times my students want to see as many examples as possible. So what I will do is I will link our normal Girls Teach Calculus video to the description of this video. And if you want, you can check out one of my former students practicing a lot of related rate questions. She does questions involving simple shapes like rectangles, but then she does more complicated situations like cars traveling or ladders again, or certain angle questions. So be on the lookout for that. I would definitely highly suggest watching that if you want more practice for related rates. But no matter what, thanks again for watching just like normal, and we appreciate your you watching this video, and give us a like and subscribe if this video was useful. Whatever you choose to do, hopefully I'll see you next time. Thanks again for watching.